Hi everybody, my name is Rajesh Jayaprakash. Thank you for giving me this opportunity to present my paper here at ELS 2020. My talk is structured as follows. First, I'll be focusing on the preliminaries. I'll spend a few minutes talking about what is partial evaluation and what is continuation passing style with an example. Next, I'll be talking about the optimization of a naive CPS transformation with an example again. And after that, I will move on to the pLisp compiler pipeline, how the CPS transform process fits within the entire compiler pipeline. This will be followed by the meat of the paper where I talk about the actual PE CPS implementation. This will be followed by a conclusion and Q&A. Partial evaluation is a compiling strategy where a program is partitioned into a static and a dynamic part. And the static part is executed at compile time so that there is less computation to do at runtime because there's only a residual program that remains to be done for execution. A somewhat simplistic and contrived example is given here where you have a small program. The code highlighted in the red rectangle is the static part. As it's obvious, the computation and the values are known right away and you don't have to wait for the program to execute to know these values. So when you do a partial evaluation, you get the program on the right where the 3 lines of code corresponding to the assignments to A, B and C have been replaced by a single number, what you see as I plus 1, 4, 2, 3, 5, 7. So this is a small example, but the principle remains the same irrespective of the language or the complexities of the programming constructs involved. Next, we'll talk about continuation passing style. Continuation passing style is where every function is passed one more argument, namely the rest of the computation, and the rest of the computation is embodied by a continuation function. So the function is expected to perform its computation, and it then invokes the continuation with the result of this computation. An example is given here, where you have an expression involving the division of x minus 1 by 2. And when you evaluate this expression, and when x minus 1 is evaluated, the continuation is the function given below, lambda v divided by 2. So the advantages of continuation passing style are that CPS makes all the control flow explicit, for example, the order of the evaluation of the function arguments. And it's also easier to introduce non-local control transfers like exceptions, coroutines, and so on to the language. So the key takeaway here is that the output of a CPS transformation is always a function, and the function invokes the continuation with the results of its own execution. A slightly a more involved example is given here, an if statement. So when you do the CPS transformation of this statement, you get the expression given below. So the key thing to note here is that the code given in the red rectangles. So each of the sub-expressions of the overall expression again get CPS transformed. So you end up with, wherever there are original expressions, you end up with again lambda forms. So it looks a bit complicated. Functionally, it is very simple, of course. It's just a simple if statement. And this code is very inefficient, and this needs to be optimized to remove all the inefficiencies, which we'll talk about next. So how do you go about optimizing a naive CPS transformation? So again, we have an example here where the expression that is transformed is plus x1, and the figure below is the CPS transformed version. So we may make use of two techniques to optimize this code. One is, of course, beta reduction, which is given here. So what you do is you have an application of a lambda expression to another expression. So what happens is that you simply replace the occurrences of v in m with n. So that's what we've done here. This is the first beta reduction. The code has gotten a bit simpler. Then we again can do one more beta reduction, the same operation as before, and yet another beta reduction. So we've done 3 beta reductions and the code has gotten quite simpler now. The other transformation that we do, the other optimization technique is inlining, which is nothing but a constant propagation of the lambda form, followed again by a beta reduction. So there is scope for us to do 3 rounds of inlining here, and we do that. And finally, we end up with a simple expression, which is the optimized version of the CPS transformed code. Okay, a sort of a sidebar here, we talk about what is pLisp. So pLisp is a Lisp dialect based on Common Lisp, and it's also an integrated development environment. And I presented this work in ELS 2018, and pLisp is available on Linux, Windows, and OS X, and it's fully open source with a GPL 3.0 license, and it's of course built using OSS components. So the motivation for pLisp is to serve as a friendly environment for beginners to learn Lisp, and the syntax and semantics of pLisp are quite close enough to Common Lisp so that people can graduate to Common Lisp once they have become exposed to Lisp through pLisp. And it's been inspired by Smalltalk environments. So there is a workspace, a transcript, and a system browser, the ability to edit code in all contexts. And we also have the paradigm of image-based development. And the pLisp GUI is also part of the image. In terms of features, it's of course a graphical IDE with context-sensitive help, syntax clearing, autocomplete, and auto indentation. And it has a native compiler, which is actually the context for this work, the CPS transformation. And it has user-friendly debugging, tracing, and as I mentioned earlier, image-based development. And other goodies like continuations, exception handling, an FFI, and a package and namespace system. Moving on to the pLisp compiler pipeline, we have these 7 steps that are the compiler passes. You start with a macro expansion where all the macros are evaluated, and you end up with a code which doesn't have any macros. Next, you do an assignment conversion where you convert all the mutable variables into mutable cells. So what happens here is that the link between a variable and its contents are always fixed, but what is stored in a content can change. Next, we transform to a simpler dialect called intermediate language, which doesn't have recursive forms. After that, we do a renaming pass where we ensure that all the variables are unique. So we use a gensum, similar to gensum technique for this. And next comes the CPS conversation, which will be the focus of this talk, where you convert the code to a convention passing style. This is followed by a closure conversion, where all the functions are converted to closures, and they start carrying their environments with them. And finally, we do a lift transformation, where we eliminate function nesting, and all the functions are taken to the top level. At the end of these 7 compiler passes, we end up with Lisp code that is semantically more or less equivalent to C code, and we use the LLVM compiler backend to convert the C code to native code. So we don't have steps like register spilling and so on in the pLisp compiler per se. Now we come to what PE CPS actually is by comparing it to a regular CPS transformation. The expression that you see on top is the one that we presented earlier for the transformation of the if expression. So you have all these various abstractions and applications which were indicated earlier. The one on the bottom is the PE CPS transformed version. So structurally, both of these expressions are similar. You can see that. But the key thing to note here is that the code that you see grayed out, I hope it's clear in the slide. The code that is grayed out is actually not generated at all, but it is executed by the compiler itself, the so-called Metalanguage interpreter within the compiler. So you have the code that is actually generated and then optimized by beta reductions and inlining and so on in the simple regular CPS transformation case is actually embodied inside the Metalanguage interpreter's code. And so you don't have to do these optimizations. They get taken care of when you actually do the compilation itself. And the only code that is left to run during execution is the one given in dark, the regular code fragments, which are actually left for the uh, program to execute. So if you look at what are the differences between a regular transformation and a PE CPS transformation. So the first thing is that the CPS transformed code is actually an abstraction in the object language. So the execution environment is aware of this abstraction and uh, executes this abstraction, whereas in the case of PE CPS transform, the CPS transformed code is an abstraction in the meta language, and the compilation process itself executes the abstraction. And in the case of regular CPS transformation, the abstraction is applied to a continuation in the object language, which is indicated by the I sub k in the previous slide. Whereas here, the abstraction is applied to a continuation in the meta language, indicated by the small m in the previous slide. And the regular CPS transformed code is made efficient by, as I mentioned earlier, beta reductions and inlining in subsequent passes. Whereas in the case of PE CPS transform, the application of the meta language abstraction already generates efficient code. So the challenge is, how do you implement the partial evaluation CPS pass in pLisp? So pLisp is written in C, and so it's imperative in style, and the functional programming abstractions that is used in the function MCPS that we saw earlier, they're not available here. So you don't have classes and things like that. So you need to mimic the OO features to handle all the different language constructs. Actually, pLisp does use a bit of C++ for the integration with the LLVM compiler, but it is not so straightforward to implement the CPS pass in C++ in pLisp, considering that the rest of pLisp is fully written in C, and so it is somewhat cumbersome thing to retrofit C++ features into the main body of the pLisp source code. So things like dispatching to the correct transformation function for each language construct, which is an automatic feature available in, say, C++, is something that we'll have to do manually in pLisp. And another thing is you have some transforms, some language constructs like let expressions, applications, and primitive operations, which may have a variable number of sub-expressions. By variable number, I mean that we do not know how many, the number of arguments that could be passed to a function invocation, for example. So there is a bit of a wrinkle in handling these such transforms in an imperative fashion. I will talk about that in detail in a subsequent slide. Again, such a transformation would have been pretty much straightforward when you, for example, want to do the whole thing in Lisp itself, for example. So since we don't have an existing Lisp dialect to bootstrap from, this option is again not available to us. Next, I'd like to spend a few minutes talking about pLisp objects and how they are internally represented. So you have these different object types that are supported in pLisp. You have integers, floats, characters, strings, symbols, arrays, the cont cells, and of course the closures and the macros, which are also actually pLisp objects. So objects are represented by the object PTR type def. It is a type def for uint PTRT, which is the the platform mechanism to store pointers. So it could be 32 bits or 64 bits as the case may be. And the last four, the least significant 4 bits of the object PTR are used to tag the object type. So you have, for example, 0001 for symbols, 0010 for stringletals, and so on. And the remaining either 28 or 60 bits are actually object specific. I'll come to that in a minute. So if it's an integer, the object specific value is the address of the allocated integer. Similarly for the float. And if it's a character, it could be the numeric representation of the ASCII value. And for strings, it's actually indexed into an array which is stored separately. And symbols, the value is split into two parts. The first part is the index into a global packages array, and the second part is index into the strings array of the chosen package array element. And for arrays, so the address of a segment of size n+1, with the first element storing the integer object denoting the array size n. And for consoles, the object specific part stores the address of the first of the two contiguous memory locations. And when it comes to closures, you store the address of the linked list of consoles that contain the native function object and the closed over objects. And macros are similar in implementation to closures. And native functions, the object specific value stores the address of the native function pointer. This is the UML model that maps the links between the objects used by the Metalanguage interpreter. These objects are not classes in the strict sense, since we are dealing with C here. So they are actually C data structures which mimic classes. There are two main so-called classes that are important here. They correspond to big M and small m. The big M represents the closures that are generated and executed by the compiler, and small m represents the continuations which the big M closures invoke after performing their own computations. And you have these entities metacont underscore fn and reg underscore cont underscore fn, which are slots in big M and small m, and which refer to abstract classes. And these abstract classes are instantiated to different objects based on the language constructs that we are dealing with. This is how the UML model translates into code. So you have these structures for both small m and big M shown here. So since both of these structures are actually closures, so you need to store the number of values or objects that each of them close over, which is shown by the field nof underscore closed underscore vals, and of course the values themselves, which is an array of object PTRs. And the first field of each of these structures, in the case of the first one, it is reg underscore cont underscore fn, and in the second case it's metacont underscore fn. These slots are the actual abstract slots which specialize to different objects based on what language construct that we are dealing with. So here's a concrete example of the transformation. We are looking at the if construct. The figure at the bottom is the same one that was in an earlier slide. So I've replaced it, I have introed it here to make the mapping between the displayed code and the actual part of the abstract function clearer. So this is basically our simulation of a dynamic dispatch. Since we don't have O features in C, so what we do is it's basically a bunch of if-then statements where each clause maps to a particular language construct. So the things to note here are the assignment to if underscore metacont underscore fn, which is the implementation for the transformation of the if construct. So what this does is it basically creates the big M closure for the if construct, and as you can see, the three closed values are the test, the then, and the else clauses. And beyond that, this doesn't do much. All the actual heavy lifting happens in the function if underscore metacont underscore fn, which we'll see next. if underscore metacont underscore fn is shown here, and the code corresponds to the highlighted portion in red. So what this function does is it extracts the closed door values corresponding to the test, then, and the else clauses from the first parameter passed to it, and it then transforms the test class into the corresponding begum closure and invokes this closure on a continuation which it builds, which is the smallum continuation. And this smallum continuation is then passed the then and the else expressions for it to close over, and then it passes control over to the smallum closure. So finally we come to the smallum closure, which is indicated in abstract form by the code snippet in the red rectangle, and the implementation is shown here of the function if underscore reg underscore cont underscore fn. So here is where the actual building of the expression that will be deferred till runtime happens. So what I mean by this is the building of the let clause with the identifier and then the if clause happens here. So that is what you see in the last line, where you actually build the code expression that will be run at runtime to realize the execution of the if clause. Before closing, I would like to show a last example how we handle let and similar clauses to let, like function applications and primitive operations, where you have a variable number of sub expressions. So the abstract code shown in the box here shows this in action, where you have all the unknown number of let expressions basically telescoping, and finally you have the last bit of code, which is the actual conversion of the body of the let. So the C code equivalent of that is shown here. So the key thing to note here is the if clause, where you have, if you have reached the last binding, then you have to treat it differently as compared to the case where you have not yet reached the last let binding. So you have two versions of the function slot here. The non-recurring version is called let cont f1 non-recur, and the recursive version is called let cont f1 recur. So a similar strategy is employed for primitives and function applications as well. The rest of the framework is pretty much the same as what I have explained for the if construct. So you have the standard bigum and smallum closures, and the way they partition the source expression into different closed values and so on. I'd like to conclude with a few remarks. So the partial evaluation based CPS transformation is significantly faster than the naive CPS with the optimizations. I actually don't have hard numbers, but since the earlier version of pLisp used to run with a naive CPS with optimizations, in comparison, the PE CPS version was dramatically faster. And the other thing is that since the implementation language is in C, so the transforms have to be implemented in an imperative style. So this took some work, simulating closures and so on. So using something like C++ would have helped in realizing these implementations more easily. And the last point is that we can explore a more declarative style of generating the transforms, where you have all these boilerplate codes which could be actually stored in an S expression template, and the execution of the metalanguage interpreter closures could just fill in these values. So that is something that could be taken as future work. So with that, I've reached the end of my presentation. Thank you for your time and patience. And I apologize for any disturbances or inconveniences in the audio. This is my first time doing a recording for such a presentation. So thanks for your time.